Okay, let's get started. We are in lecture 25. I was looking at our remaining lectures, and so if you eliminate the second and third exam, you eliminate the exam reviews, and then like our days where we're just working on our project submittal, we only have like 12 topic lectures left. It's crazy, isn't it? We are in the middle of it. Okay, just a heads up on housekeeping. Attendance grades are up to date. Homework grades are up to date up through 5.6. 5.7 is still being graded. How did the deflection homework go? Hopefully that one was short. Next one's not going to be. I'm just going to tell you. Which is why I'm giving you until Monday to do it. Okay. Now the way the deflection homework is going to go, I'm assigning it today. And then on Friday what I'm going to do is go through some strategies to make your life a little easier doing that homework assignment. So maybe a piece of advice would be for between now and Friday to at least have all of the moment diagrams constructed, because it will help you in doing the problem. Maybe hold off a little bit on all of the function generation, because there are some tricks that you can use to make that a little bit easier. Again, I'm still working on the grading of submittal 1. My goal is to get that done either Friday or Monday, but definitely by Monday, because Monday I'm going to give you submittal 2. Okay. Homework 6.3, just so you are aware, is the homework. The only thing that you have to do for homework 6.3 is install Masthand. Okay. If you go to Blackboard now, you should see the link for installing it. You should go ahead and do that. There are 2 ways to install it. One if you have MATLAB on your computer, and one if you don't. And considering that civil engineers tend to view MATLAB the way vampires view garlic, I'm guessing that the moment you left Engineering 111, you uninstalled MATLAB and you're like, I'm never looking at MATLAB again. And I rue the day that I ever had to look at it to begin with. How am I doing?
Sounds about right.
How am I doing? So, don't worry. You don't have to use MATLAB. Don't worry. But there is a standalone version of Masthand. But homework 6.3, all you have to do is upload a screenshot saying you installed it. And I'm doing that just to make sure that when we start doing Masthand, that we all have it ready. Okay, and it's Windows and Mac friendly. So, sound good? Okay, so today we've got an example to get through today. So I kind of really want to just get right into it. Okay. So just to make sure that we're clear on what we're doing today, so the last lecture and the homework that you all just did was focused on problems that involved single moment functions. So we had a beam both on your homework and in class where there was a moment diagram for both the real structure and the virtual structure where you're only required a single moment function to define that moment diagram. And that's not going to happen today. Today we're going to have multiple moment functions. Okay? Now just to make sure we're clear on the process, what we're going to be doing is writing both real moment functions and virtual moment functions for the entirety of the structure, and then summing up the integrals of little m big M over EI. So last time we just had a single integral that we integrated across the entire span. That's not going to happen today. We're going to have multiple integrals that we need to evaluate. Okay? And so the best way of learning how to do that is to just go through a problem. Okay? So to give you an idea of what I'm talking about something like this. So we talked about this problem last time where, remember the trick where you would just almost just like take a sheet of paper and start here and work your way over, and then it would tell you how many moment functions you would need to fully define the moment diagram. We did this problem just as a thought experiment, and we found that we needed 3, right? Well, this is the moment diagram for this structure, and you can kind of see the 3 functions. We have sort of this cubic function, parabola, cubic function, right? And so the idea is that if you wanted to fully define the moment diagram, we would need the equation for this curve, the equation for this curve, and the equation for this one. Okay, so that would be our real moment diagrams. We would have 3 big M functions. We might have some little m functions as well, and then we would do our integration accordingly. And I'm using the term like do our integration accordingly a little loosely. You'll see what I mean today, like with this example. And so speaking of, let's just get right into it. Okay, so I have a fairly straightforward beam. I have a simply supported beam with a uniformly distributed load. I've given you the Young's modulus and the moment of inertia. So if For E is 4,000 KSI and a moment of inertia of 6,000 inches to the fourth. We're talking about a beam that is probably a concrete beam. Okay, so this is a beam that's 4,000 KSI, Young's modulus, so what is it, 57,000 square root of FC prime? Are y'all doing that in 321 yet? So you've seen that formula before. So yeah, so about 4,000 KSI for E, 6,000 moment of inertia, and we have 1.2 kips per foot over a beam that's 30 foot long. So just making sure we're on the same page, how many real moment functions will I need to fully define the moment diagram? How many real functions? One, right? Because if I cut a section here and look to the left, no matter where I cut, I look to the left, I have a distributed load and a reaction. Okay? So we're only going to need one real moment function, but that's not going to be the case with the virtual functions. Okay? So let's get right into it. And I've got a couple things open here down below, and I'll explain all this stuff as we get into it. So okay, so the first thing that we'll do is we'll handle the real structure. Okay, so and the first thing that I would suggest is going through and doing the structural analysis normally. So drawing the shear diagram, drawing the moment diagram graphically, so you can get kind of an idea of what you're looking at. Okay, I think that's really important. So we've got a simply supported beam. We've got a uniformly distributed load. So this is 1.2 kips per foot. Bless you. We have a hinge support. We have a roller support. All right. Now, how many reactions am I going to have on the, how many vertical reactions do I need to solve for? Totally. 2, right? One here and one here. Can somebody look at this structure and tell me a characteristic about these 2 reactions? They should be equal, right? This is a symmetric structure, right? And we're going to talk on Friday a little bit about exploiting symmetry and how symmetry can make your life a lot easier when doing virtual work problems. But the point I'm making is, again, this is a symmetric structure, so these reactions should be equal, okay? And can anybody just offhand tell me how much the reactions are if this is a 30-foot long beam? Right? And it's 30 feet because if we look here, 10 and 20, so the beam's 30 foot long. How much are the reactions? 18 kips. Do I have a second on that? Yes, because what we can say is by symmetry, we can just say that the reaction is 1.2 kips per foot over a distance of 30 feet, and then we cut that in half. So that's 18 kips. That should be easy at this point, right? Is there anything that's pretty straightforward, right? Okay. We haven't really done problems like that. We've been pretty formal about it up until now, where we write our equations of equilibrium. But we are engineers, and so just using your engineering judgment, that's going to be 18 kips. Okay. So now I'm going to, so here I'll put 18 kips, 18 kips. Let's go through and draw our shear and moment diagrams. So somebody tell me the shear diagram. So if I start at 0, bless you, if I start at 0, what does the shear diagram look like graphically? What's the first thing I do? 18. And then what's it going to look like from 18 all the way over here? It'll be sloped down to negative 18 and shoot back up to 0. It's exactly right. So it's going to look something like this. About like that. And this is 18, this is negative 18, and then we shoot back up to 0. Exactly right, okay? And just so we're paying attention, what's the slope of that line? There you go, 1.2. Okay, so if the beam is 30 foot long, how long is this? 15. So if that's 15 feet, what's the area under the shear diagram? What are the areas of these 2 triangular regions? 135. 135. Do I have a second? Yes. All right, so this is plus 135. This is minus 135. So that means our moment diagram, what is our moment diagram generally going to look like? A parabola opening downwards, right? It's going to open downwards, and it's going to peak right here, right? Because it's going to go a lot to a little, little to a lot. It's just going to be one big parabola that just happens to peak right here. How much is that peak? 135. So our moment diagram is going to look something about like this. So we start at 0. Something about like that. So when writing our moment function, so let's just make some observations. Here, I'll do it here on the screen. So what observations can we make about m of x before we even start doing the math? Like, don't worry about deriving equations just yet. Let's just use our noggins, okay? So first off, I think we can say it's a parabola, right? Right? We can also say it opens downward. What does that mean? That means we're going to have a negative x squared term in it, right? Is everybody okay with that? Okay. How about this? All right, let's just abbreviate that. How about that? That the function has to equal 0 at x equals 0 and x equals 30, right? Okay? The other thing is we know m of 15. That's going to be m max. And it's also going to equal 135. So I didn't derive any equations. No x's yet, no clean sections. I'm just looking at the structure, looking at my moment diagram, and making some common sense observations. Everybody with me on that? And maybe one other point I would mention is it's a single moment function. All right. So now, with that being said, now let's cut a section. And what I'm going to do is I'm going to cut a section, and I'm going to look to the left. Okay? Now, I'm going to make a note about something. One of the things that I, again, was very fast and loose about is I didn't draw my coordinate system. Okay? I didn't draw the coordinate system. I gave you the coordinate system on this problem, but I'll tell you on your homework assignment that I'm giving you, it's not given. Okay? So you're going to have to figure that out. And that's going to be part of what we discuss on Friday. But I'll make another note. I'll say note. And I'll say, woo, it is often advantageous when cutting sections to look towards the origin. More on that later. Now, I chose my words very carefully there because I did not say it is advantageous to cut a section and look to the left. I said cut a section and look to the origin. Those aren't the same things, okay? And you might be a little confused about that. Don't worry, on Friday that'll make sense. Okay, so now what I'm going to do is I'm going to cut. Now let's actually do our section cut. So let's cut section 1-1, look to the left. And so here's our section cut. Which way is positive shear? Down, there we go. And positive moment is going to be like that. And we have our reaction, which we now know, which is 18 kips. And what is this distance?
X.
X. We are defining a moment as a function of x. Okay? So I'll move this down just a little bit. Okay? So I'm going to collapse that into a single point load. How much is that point load?
1.2 times x over 2.
No. It's not a triangle. I have 1.2 kips per foot over a distance of x feet. The load is just 1.2 times x. The moment arm from here to here is x over 2. Does that make sense? So this is 1.2x. This distance, x over 2. Does that sound good? Are with me on that? Okay. So now we're going to sum moments at the cut. Oh. All right. So, and as I'm going through this, if I'm going too fast, you tell me. Okay. So I've got 18 times x, 1.2x times x over 2, and then m. I don't need to consider the v because the v is going right through the cut. So I'm going to have 18x. Nope, that's not an exponent. 18x, and then 1.2x, x over 2, and then m. Okay? So 18x, I'm going to move that up a little bit because I want this all to be on the same screen. So 18x is m plus what? What is that? 1.2 over 2 is that 0.6x? Is it 0.2x or 0.6x? Or is it 0.6x squared? Don't forget that exponent. It's 0.6x squared. So therefore, m is 18x minus 0.6, sorry, 0.6 x squared. And what I'm going to do like last time is I'm going to put a limit and say 0 to 30. Okay? And today, that will make a lot more sense. Crossing through it. Okay. So let's sort of take this in a little bit, okay? Did our observations hold true? Well, let's see. It's a parabola that opens downward. And if it's a parabola that opens downward, we said the x squared term would be negative. Is the x squared term negative? It is, right? What happens if we plug in x equals 0? What do we get? 0. What happens if we plug in x equals 30 or x equals 15? Better yet, we have this little handy tool called Microsoft Excel. Let's bring out Microsoft Excel. So I set some stuff up right before class, so let me show you what I got going on. I've got an x column that goes from 0 to 30. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then the 10 is repeated. And you're like, why is the 10 repeated? Don't worry, it'll make sense later. But what I've got is an m column, and then we're doing displacement and rotation. So I've got 2 columns for the virtual function. Let's start plugging and chugging. So what did we say? We said, what did we say? Equals 18 times x minus 0.6 times x squared. And then, come on. Boom. Does that look right? Well, we've got a 0 here, a 30 here, the max at 15. What is the value at 15? It's 135. Everything's looking like it's making sense, right? You got this wonderful little tool. Make sure that you avail yourself of it. Okay. Does that make sense? So now we have our real moment function. So we have our real moment function. I'll put it up here on the board. So we'll say that m of x is 18x minus 0.6x squared. We evaluate that from 0 to 30. Okay, so now we're going to do little m of x. Now what I'm going to do is I'm going to say, okay, we've got little m of x, but I'm going to call it little m delta because the problem, we're finding two deformations. We're finding a displacement and finding a rotation. So if we go back to the problem, what did the problem say? We're going to try and define the vertical deflection and rotation at point B on the beam shown using the principle of virtual work. Okay? So now what we're going to need to do is a virtual analysis. Let's do the deflection first. Let's do the vertical displacement first. So we'll find these m deltas. So what we're going to do is we're going to find the vertical deflection first. So the way that works, we kick all of the original loads off the structure, right? And we replace it with a single unit load in the direction of the assumed displacement. On this structure, which way do you think B is going to deflect, up or down? Down. So we're going to do our virtual structure like this. So let's go back to this. Does everybody have all this written down? I got this? Okay. So now go a little further. All right, okay. All right. So vertical or virtual structure. Now let's do vertical deflection at B. Okay? So we've got a structure that looks like this. Oh, I can do better than that. We've got our support here. And B was about right there. That's where point B is. And we replace that with a single unit load. So if you want, you can think of it as like a one kip load. Really, it doesn't have units, but if you want to think of it as one kip, that's fine. We have a one kip load, and that is placed such that this is 10 feet, and this is 20 feet, right? So this is my x-axis, this is my y-axis. So we're going to have a reaction here and a reaction here. Maybe what I'll do is I'll call this AY and CY, but I'll use lowercase letters because it's sort of a virtual structure since we're using lowercase for everything. So what I'm going to do, the way I'm going to handle this problem is I'm going to draw the shear and moment diagrams, and I'm going to draw them graphically. Okay? So first thing I need to do is I need to compute the reactions. So I'm going to sum moments at A. Okay, so if I sum moments at A, what do I have? I sum moments, I've got 1 times 10, and I've got CY times 30, right? CY times 30. So I've got 1 times 10 times 10 feet is CY times 30 feet. Is everybody okay with that? So 10 feet is CY times 30 feet. So CY is a third, right? Did I do that correctly? So a third. Okay, so we'll say CY is a third. So equals. So if I sum forces in the x direction, or sorry, in the y direction, y'all help me out. What is AY? There you go. AY is 2/3 going up. And again, it's not 2/3 kips, it's just 2/3. You know, again, if you want to think of it as a kip, that's fine, but it technically has no units. Okay. So now what we're going to do is graphically construct our shear and moment diagrams. So let's start off with the shear. So the shear doesn't have any units. So we start out at 0. So somebody tell me what to do. Start here, what do I do? Go up how much? Then what do I do from here to B? What do I do?
Straight across.
Straight across, and then I
Down 1.
2,
Negative 1/3.
then over 2, and then back up, right? So our shear diagram should look something like this. All right, so and again, the slope of these two lines are 0 because the slopes are 0 because there's no load in these sections. Okay, what are the areas of these two rectangles? 2/3 times 10 or negative 1/3 times 20, or 20/3, right? 20/3 is about what, 6.67? So let's just put that here. Okay. So we'll say plus 20/3 minus 20/3. And so our moment diagram start at 0, jump up to 20/3, back down to 0. With me so far? Okay. So far so good. Now one final question. What's the slope of this line and that line? What's the slope of this one?
2/3.
And this one?
Negative 1/3.
Okay, all right. Okay, so with that, I'm going to move these up a little bit. Oh. Let's make some observations about M delta. Let's make some observations, just like we did last time, okay? So last time we had a parabola that opened downward. Do we have that case here? So here what we have is a piecewise linear function. And specifically, we're going to have two equations, right? We're going to have one, so we'll call it M1 from 0 to 10, and M2 from, sorry, but not 20, 10 to 30. Does that make sense? Remember my Excel sheet? Remember how I said I was repeating the 10 twice? Now you can kind of see why I did that. You'll see what happens here in a second. Okay, so we have a piecewise linear function. Okay? And so what I'll do is I'll do this. So let's look at M1 and let's look at M2. What's the slope of M1?
2/3.
It's 2/3. The slope of this line is minus 1/3. Is that a fair statement? Okay. Now, remember my coordinate system. What is a point that this line goes through? Give me a point that this line goes through. A simple point to deal with.
20/3, 10.
Okay, 20/3, 10. What's an easier point?
0, 0.
0, 0. So what is the y-intercept of this line?
0.
So therefore, M1 is 2/3 x. Y equals mx plus b. That's the slope. That's the intercept. Y equals mx plus b. And this is from 0 to 10. Sound good? Okay, now this one, okay? Now you mentioned 20/3 or 10 and 20/3 as a point that this goes through. But I don't know about you, I kind of like dealing with zeros. Let's talk about this point. Is there a point that this one goes through that's easy to deal with? 30, 0. So this point, so I'll say goes through 30, 0. And so if you want, what you can do is say, okay, y minus y1 equals m times x minus x1. Just sort of do that off to the side. Y minus 0 equals negative 1/3 x minus 30. Y equals negative 1/3 x, what is that, plus 10. Right? So if you want, you can say, therefore, M2 is 10 minus 1/3 x from 10 to 30. So what we can do is we can write this as make that a little better. Right? Does that work? Do those equations work? Well, let's see. So we've got two-thirds times x. Zoom out a little bit. So we're going to use that until we get right here. That one needs to go over there. So, and then here, 10 minus like that. Down. Okay? Again, right here we get the same value on both equations, right? So if we highlight this, you know, this point's kind of special because we get, you know, with one equation and the other equation, we get the same answer, but this is where the equations transition. Does that make sense? And so we can graph it out and see that it makes sense. Okay. Any questions? So now it's time to actually find a deflection, okay? And so how do we do that? Well, we use the principle of virtual work, okay? Okay? And our principle of virtual work, we'll call it deflection at A, or sorry, deflection at B. We're finding the deflection at B, right? Deflection at B, and we're finding vertical deflection. The principle says that we need to sum up our integrals, right? Okay? So, but let's just make make sure we understand what we're doing. What we're trying to do is we're trying to sum up all of the stored energy inside the beam. Remember, virtual work is just a comparison between external work done and stored strain energy. Okay? So we need to sum up the little m times big M across the entire structure. The problem is we have two little m functions. This little m function is only valid from 0 to 10. Like the big M works for the whole structure, but this one's only valid from 0 to 10. This one's valid from 10 to 30. So the way that we're going to have to do this is we're going to have to say, okay, I'm going to have one integral that goes from 0 to 10. And then I'm going to have another integral that goes from 10 to 30. And then don't forget, I want to multiply the whole thing by 1728. Does that make sense? Does that make sense? So far, so good? So what I'm going to do now is I'm just going to do some substitution. Now, I'm going to use some rules of calculus. Both of these expressions are divided by EI. And EI was a constant. EI is 4,000, I is 6,000, or E is 4,000, I is 6,000. So I'm going to pull the 1728 over EI outside. So I've got 1728 over EI I'm going to have an integral from 0 to 10 of, and I'm going to have 2/3 x times that dx plus, and then I'm going to have another integral from 10 to 30 of 10 minus x over 3 times 18x minus 0.6 x squared dx. Okay? Now, my question to you as the class is, so let's look at this. That should not be anything that you can't handle. Am I right? Right? And to be clear, I don't even really expect you to do that, right? There's nothing to say you can't just, I mean, you have tools. Use them, right? In fact, this is this integral. So if you integrate this from 0 to 10, 2/3 x times that, and plug and chug, you get an integral of 3,000. So this integral is 3,000. This integral, I'll go ahead and tell you, this integral ends up being, when it's all said and done, 8,000. Okay? So therefore, the deflection is going to be 1728 times 3,000 plus 8,000 all over, and then we have E is 4,000. This is 6,000. And I am being kind of fast and loose on the units, but again, we derived this unit conversion factor such that if all of our inputs were in our chosen unit system, then the output would come out the way that we wanted. So it kind of works out for us. And when you chug this out, you should get 0.792. So therefore, delta By is 0.792 inches downward. Okay. I want to take a step back. Let's digest what we've done here. Does anybody have any questions on this? Anybody have any questions? Sound good? Okay. Now, we have another deflection that we need to solve, and I'm going to go through this one a little bit faster. But so we're going to do another one where we find functions for m theta. Now I'll go ahead and tell you we are going to have a similar sort of function for 0 to 10 and another function for 10 to 30. But let's sort of walk through how we do that. Okay? Now, in order to do that, let's just sort of use some common sense. Okay, so here's the beam. Would you agree that, okay, let's go back to the original structure. So this is the original structure. Okay, so the original structure had loads like this, going down. Would you agree that the structure's deformed shape, something about like that, for the most part? Like, doesn't have to be perfect, but you agree it's kind of going to deform something like this. So we're looking at like that point right there on the structure. What we just found was delta B. Like, we just found that, and we just found that it was about 0.79 inches. Now what we're going to do is figure out the rotation at B. So in other words, what is the slope of that line? Okay? So the idea is, like, here's what the beam used to look like. Here's what it looks like now. So I'm proposing that it rotates like this. So what that means is that when I look at my beam, I'm going to put a moment on the beam that looks like this. That's why I'm going to put the moment in that direction. Okay? So when I look at my virtual structure, so let's draw that out right here. So we'll call this virtual structure. Let me go down a little bit. Where'd my scroll's not liking me. Okay. So what I'm going to do is I'm going to pick, that's the point, and I'm going to put a unit moment. Now, to be clear, if you do this analysis and you choose the wrong direction, like instead of having the moment rotate clockwise, if you put the moment rotating counterclockwise, if you assume incorrectly, what's going to happen at the very end? Say it again. You're going to get a negative answer, right? So if I'm putting it clockwise. If you put it counterclockwise, you're just going to get a different answer, or a negative answer. Doesn't mean the magnitude's going to be wrong, just a negative answer. Okay, so let me walk you through this one real quick. I don't think we're going to get to finish the problem, but I'll at least get through the difficult parts. Okay, so don't forget we've got our coordinate system right here. And so, like last time, what I'm going to try and do is I'm going to try and solve for the reactions. Okay? Now, I propose that the reactions are going to look a little different. I propose I'm going to have a vertical reaction right here going up, but I propose this one's going down. Okay? And if you're wondering how I'm coming up with that, so I've got this moment. This moment is wanting to rotate the structure this way, so I propose the reactions have to rotate the structure the other way to keep it in equilibrium. That's kind of the idea. But if you don't believe me, let's do the statics, okay? So let's recognize again, this is 10 feet, this is 20 feet. Okay, so 10 and 20, okay? So what I'm going to do is I'm going to sum moments at A. Okay. So if I sum moments at A, I have this unit moment. So I have 1 times what? Nothing, right? It's a moment. You don't multiply it by a moment arm. You just do 1, right? Because you're just summing moments, right? So I have 1 right here, and here I've got CY times 30. Now I'm putting it on the right side because here that moment rotates like this, okay? So I've got 1 equals cy times 30. So therefore, cy is 1 over 30. So this is 1 over 30. But here's the thing. If that's 1 over 30 going up, what does this have to be in order to maintain vertical equilibrium? This has to be 1 over 30 going down, right? So that's where I have the two equal and opposite reactions. So this 130 going down. So here's what our diagrams are going to look like. Let's do that. So when I do this, we'll draw this line here too. So when I draw my shear diagram, what's going to happen is I'm going to start at 0. I'm going to drop down to negative 1 over 30. But what's the shear diagram going to look like from start to finish? It's just going to be flat because that moment does not affect the shear diagram. Okay. All right. So far, so good? Now, I am going to break this up into different segments so that we can negotiate this. This is going to be negative 1/3, this area, and this one's going to be negative 2/3. So what I'm doing is I'm splitting it up along that line. So the total area under the shear diagram is negative 1, right? So that moment has to cause a sudden increase in 1 in order to get us back to 0. See, my moment diagram is going to look like this. So I'm going to start at 0. I'm going to drop down to negative 1/3. I'm going to shoot up to positive 2/3 because that's where my concentrated moment is, and then go back down to 0. Okay? And by the way, what's the slope of these lines?
Negative 1/3.
Negative 1/3 or negative 1 over what? 1 over 30, right? It's the shear diagram, right? So this, negative 1 over 30, this is negative 1 over 30, okay? So just to bookend this, and I don't think we're going to finish the example today, but I think we'll be able to at least make our observations. So just like last time, we're going to have piecewise linear functions. We're going to have two equations, and we're going to have M1 from 0 to 10 and M2 from 10 to 30. Now, we're not going to be able to finish this today because I'm not going to try and keep you over too long, and I don't want to rush this. But if you're interested in sort of toying around with this on your own, what I'll tell you is that this one ends up being negative 1/3 x. This one ends up being, let's see, 10 minus x over 3, I think. Yeah, yeah. Or no. There's a, no, this is 30, x over 30. long story short, the theta, we'll look at this next time. The theta is 0.224. But we'll finish this next time. And then next time what we'll do is we'll do our tips and tricks lecture. I don't want to rush this. I want to take our time with it. So let's take our time with this, and we will discuss this. We'll finish this up on Friday. I'll pull up the code in case you missed it, and I will see you all on Friday.